Hi again, Mr. Nichols here, and today we're going to look at solving vertical accelerated motion problems with the principal focus on what is called free fall. And that can happen either when an object is moving upwards, away from the ground, or when it is falling downwards towards the ground. Both of those are considered free fall in that the only acceleration acting on the object is the acceleration of gravity, or the planet's pull of gravity acting on the object, which causes it to always act so that its acceleration is in the downward direction. Now essentially what this means is, if we look at it very simply, is a long time ago, Galileo Galilei did experiments over in Italy, and he dropped objects of very different masses from whatever was the top of the Tower of Pisa at that time. I can't recall if at that point it had been fully constructed or not. Let's just assume it's leaning, because that's the way the Bugs Bunny cartoons always show it. But he had objects of very, very different masses, like 10-to-1 mass differences. And within reason, the ancient thinking was that an object with more mass was more attracted to the Earth than an object with less mass. And the rate at which it fell was proportional to the difference in the masses. So 10 times more massive object should accelerate towards the Earth with 10 times more of a rate, so it should get there faster. And that was not seen. There was obviously some differences, but he was really a proponent of the acceleration of these objects is a set value. And with the limited resources he had, he couldn't test things like they can in vacuum chambers and things. But pretty much a very simple experiment, you could see that these things were falling at about the same rate. So they were independent of mass. So something was acting outside of the object. That turns out to be the gravitational pull of the Earth acting on another mass, which causes the mass to be attracted towards the center of the Earth. So for us, it's going to always look down, and that's how we take it. So the acceleration of gravity, when we look at it, we use the expression of a little g, which stands for the gravitational acceleration at or near the surface of a planet, and it is set, or not a set, it is determined to be the value of 9.8 meters per second squared down on Earth. In the problems we calculate, we're going to use -10 because it's easier. But think about what this means. Regardless of the way the object travels, whether it's a positive velocity upwards or a negative velocity downwards, that is saying that this object will always have an acceleration rate of 9.8 meters per second squared down. Now what that's going to mean is you have to think back to everything you've seen in the world around you. When things travel up, they slow down, they reach a maximum height, and then they come back down. And when they come back down, they start speeding up. So the motion that you see takes place because the gravitational acceleration only is in one direction in terms of its rate of change. So if you have a -9.8 acting on the object as it's traveling upwards, well, that's a slowdown. We've talked about that. When you have a negative acceleration and a positive velocity, that's an SD, that's a slowdown. When you're at maximum height, well, this thing has just run out of gas, so guess what? It's just going to fall back down because the gravitational acceleration, it's constant. It's there every moment of the day. The thing just doesn't float there. So if the acceleration is downward and it has initial velocity of 0 at that point, it's going to move this way, and it's going to start speeding up. Well, if you have a negative velocity and a negative acceleration, that's a speed up, and it's in the negative direction. This is the way free fall happens when you look at the vertical motion of an object on the Earth. That is kind of the reasoning behind why this value is a set number. When we get into forces, we will look in more detail as to why that number happens, the value, and what happens on a level where, what if we change the mass? Why doesn't it cause a larger force? Well, it does, ... But I'm going to leave that for when we get to forces. So we're going to look at doing free fall problems here. Specifically, a motion down, like a free fall, a drop, and then an up and a down. And that's probably where I'll conclude this lecture. So let's move on from here. If in a problem we have a ball is dropped from a height of 43 meters, determine how fast it's moving before impact, and then determine the total time the ball is in the air. Well, we got to kind of set this up, and again, I'm going to draw a quick picture and say, okay, I have a ball, and it is 23 meters above the ground. And as soon as I know I'm dropping something, that is a code for, not that, it's a code for acceleration is negative 9.8, but because we're going to do word problems make life easy on you, the acceleration of gravitation, because we're looking vertically, is negative 10 meters per second squared. Doesn't matter which way you're moving, it's always going to be a negative 10. So there are a couple of other keywords in here. It's dropped. Guess what? VI is 0. Height of 43, that's going to be your delta x. Don't get confused. X is just displacement. It's just going to be a variable. We're going to use x to mean vertical as well here. How fast is it moving before impact? That's going to be my VF, and then determine the total time. So let's clean this up and see what's going on. So I'm going to leave my little caricature there. And directionality is really important here, guys, when I'm setting up my list. So if I start to list things out, as soon as I realize it's a free fall problem, all right, I'm going to write this first because I just don't want to forget it. A is negative 10 meters per second squared. My initial velocity is 0. It's being dropped. My displacement, now be careful here, guys. This is falling. And what that means is this is a negative 43. The ball is traveling downwards 43 meters. We're solving for VF. I'm going to go after the velocity and the time. So that's the stuff I'm trying to solve for. You can solve this in a couple of different ways. Having the displacement is really critical here. So let's see. If I go after the final velocity first, what can I do with that? I guess I can try the VF squared equation. I'm just trying to think of how I'd approach this. I have acceleration, so VF. I don't have time, and I don't have VF. So my first equation is out. That doesn't help me because there are two unknowns. I need VI, VF, T, and delta X to use the second one. I've got delta X, two unknowns again, so goodbye. And VIT, 1/2 AT squared. Can I use that? Let's see, I've got the X. The VI is 0, great. Yeah, I'm going to try that one. That will give me the time. The time is in the air. Or I can use the VF squared. I think it depends on how you want to approach it. I'm gonna go after the total time first. You can kind of choose how you want to do this. But I'm going to look and say, if I know the displacement, I'm using equation 3 now. VIT plus 1/2 AT squared. Well, I know this thing is falling 43 meters, minus 43. My initial velocity is 0, so that's gone, nice and easy. Now start to notice this, guys. 1/2 times the acceleration of gravity. You're always going to get a minus 5 out of this term. Always going to happen. And then t squared. So we have minus 43 equals minus 5 t squared. So move that up. Now we have negative 43. The minus signs are really important because we can't have a negative time. So negative 43 divided by negative 5. We're going to take the square root of that guy to get the time. This is going to be equal to 2.93 seconds. So I answered the last question first, just to show you can kind of work around these. Now it wants to know the final velocity as well. So let's get after that and we'll be done with this first problem. I'm going to go right after it and I'm going to say, all right, VF equals VI plus AT, because I can absolutely use that now. Now VF equals, now the VI is 0. Be careful here. A is negative 10. Time is 2.93. So my final velocity, I'm going to ask you to make sure you get the direction right on this. Negative 29.3, that's fine, take it to that point. meters per second. So that is a velocity just before hitting the ground, negative because it's falling down. Okay, so that's how you would do a dropped object calculation. Now, could you have used the VF squared equation first to solve for the final velocity? You absolutely could have done that. You could have basically said VF squared equals VI squared plus 2A delta x. The VI is gone. Now this is where you got to be careful. This is where the double negatives help you. Negative 10, negative 43. And that's VF squared. So if things are right and you finish the work on this one, you're going to end up, now here's the catch though, guys, so pay attention, so listen closely. When you take the square root of that VF squared, it's always going to give you by default a positive number. If this thing is falling down, you have to make sure your thinking cap is on and you put this as a minus value. So that VF squared, that is the one bugaboo with that is when you take the square root, it has to be a positive number so it doesn't let you know whether the value is negative or positive. You'll have to look at what's happening and decide on which way it's moving.